Look up at the night sky, and it feels like you're seeing the whole story. Billions of stars, sprawling planets, entire galaxies stacked on top of one another. But if we pull back far enough, everything humanity has photographed or mapped constitutes 5% of the universe. The other 95% is a total void. In astrophysics, being invisible means light passes right through this missing matter. It doesn't absorb, reflect, or emit photons. This immense shadow exerts a physical presence, possessing a gravitational pull strong enough to dictate how the rest of the cosmos behaves. Relying on light to understand reality means we're only looking at the universe's surface. To find the missing 95%, we must stop looking and start tracking the gravity. In the 1930s, an astronomer named Fritz Zwicky noticed a glaring math error in the sky. Zwicky was observing the Coma cluster, a massive grouping of galaxies. By measuring the combined starlight coming from the cluster, he could estimate its total mass. But the numbers didn't add up. The galaxies in the cluster were moving at velocities so extreme that their own visible mass couldn't possibly generate enough gravity to hold them together. By all rights, the cluster should have torn itself apart. Decades later, astronomer Vera Rubin discovered this was a universal rule. She scaled down from massive galaxy clusters to look at individual spiral galaxies. This graph plots a spiral galaxy's rotation speed. Physics dictates that outer stars should orbit much slower than the dense visible center. Instead, Rubin observed them moving far too fast, tethered by a massive unseen weight. These escalating mathematical impossibilities prove the necessity of a massive invisible anchor, dark matter, holding all galactic structures together. This creates a unique problem for astrophysicists. How do you map the exact location of an entity that is completely immune to light? This diagram illustrates the mechanics of gravitational lensing. When an incredibly dense mass of dark matter sits in space, its gravity warps the geometric fabric of the space itself. When a straight beam of light hits that warped space, it is forced to curve. Because of this bending, the light from distant quasars gets stretched into visible rings and arcs. Instead of seeing dark matter directly, astrophysicists map its gravitational footprint by watching it distort the visible universe behind it. Once we trace these gravitational footprints across the entire observable sky, a new picture of reality emerges. A moment of wonder. We find the cosmic web. These are continuous, universe-spanning filaments of invisible dark matter that form the architectural foundation of the cosmos. The 5% of matter that we can actually see, the stars and galaxies, are merely trapped byproducts. They pool and collect within the deepest gravitational wells of this dark matter web. Dark matter serves as the primary architect of the cosmos. Visible galaxies merely settle into the depths of this invisible scaffolding. We know exactly how this invisible scaffolding behaves on a macro scale. Yet down at the quantum level, physics still cannot identify what a dark matter particle actually is. The physical hunt for that particle relies on deep underground research facilities, shielded by thousands of feet of solid rock to block normal cosmic radiation. Other teams take an active approach, using massive colliders to forcefully smash atoms together, hoping to generate a detectable interaction with a dark matter particle. It requires an immense density of engineering just to try and capture a singular, microscopic anomaly that refuses to interact with the electromagnetic spectrum. Human eyes evolved to detect only a fraction of reality. Gravity governs the universe that light cannot reach. You see 5%. Gravity feels the rest.